that, we finished the basic structure of how to build a RISC-V machine with its base instructions and to understand how C kind of maps to the hardware. But I wanted to introduce a number of features and extensions that RISC-V has just to finish this point. So a note about the ISA in general, because I've mentioned it already, but you'll also run into this if you start to use something like RISC-V. So it has something called the base integer ISA, which is called RV32I, I for integer. That's the 32-bit version. There's also a 64-bit and even a 128-bit specification. And this is the base integer, which means it must be present in any implementation. And I'll just say something about that because it's not exactly accurate. But in general, that is the frozen type of basic RISC-V that will be around for forever, basically. It cannot change. That's the basic integer ISA, and that is really present in any implementation of RISC-V. But in addition to that, RISC-V was built from the bottom up as what is called an extendable architecture. And that means you can do all kinds of things to create additional instructions. And there's actually something called standard instructions, which are, for example, the M, A, F, and D, where M is integer, multiply, divide, and remainder. A is atomic memory operations. F is single precision floating point. And D is double precision floating point. And if you just want to make an implementation that has M, A, F, and D, you can just write RV32G, and that means it has all of them, instead of kind of concatenating all of these letters one after the other. So there's another very commonly found standard extension, which is C, which are compressed instructions. And this lets us have 16-bit encoding for real frequently used instructions to save code space. And we have something that I said it's not exactly true that it's present in any implementation, because there's an embedded version, which is really a smaller subset for small microcontrollers, and it won't implement the entire RV32I, but everything else will, except for the less common E extension. So if we want to look at the kind of schematic of how you could implement the full base architecture, we can look at something like this. So we have the program counter, which is driven to the instruction memory as the address, and that will bring us out the instruction. In addition to that, we'll take the program counter and add it with 4 to increment to provide us the next instruction along the way. Out of the instruction itself, we decode it, and we can get, the two source operands and the destination operand, or the immediate, which will also be sign extended. And we can take the data that's read out of these registers, and we can use them as operands for the ALU, and the second operand can either be from the immediate or also from the ALU. We can also provide our displacement addressing using the result of the ALU, and we can also get our write data from over there. And then we can either take the output read data for a load type of operation, or directly what we got out of our ALU and then write it back into the write register. We also can take the immediate, shift it left, and add it with the PC for our displacement type addressing, and this is for breaking the control flow and changing our PC. So that's pretty much our basic, full base architecture data path. One thing that we can do there is then add kind of the control. So for example, we know that the opcode is always going to be residing in the 7 bottom bits, so that we can put into some sort of a combinational control block and get all kinds of other signals that can actually set these muxes and set what happens in the ALU and so forth. And we can take other bits and parts of the instruction and do things like ALU control and so forth to get like this whole base kind of architecture data path. And you can easily make such an implementation. Again, RISC-V is a specification of the architecture, and it doesn't go into the microarchitecture. And you can do this in many ways, but this is kind of just one possibility, a simple possibility of breaking down how you take the base integer data path and turn it into like a microarchitectural schematic block. So what other features can we talk about with RISC-V? First of all, that it's little endian. So I mentioned it before, but it does not support big endian. If you want to do that, you'd have to do it with an extension. It does not require words to be aligned in memory. So other architectures will require word alignment. So every instruction would have to start at a 32-bit alignment. But here actually we have, 16-bit compressed instructions, which we'll discuss in a minute, there is no requirement to have words aligned in memory. There are no branch delay slots. So I don't know if you've learned about MIPS, but that's often used in different types of basic computer architecture courses as an example, ISA. And it's very similar to RISC-V that I used here. But one of the big differences for MIPS is that RISC-V did not require a branch delay slot as was originally required in MIPS and later on removed. So that's kind of a big important thing that they did not take into RISC-V. There are no overflow checks on integer arithmetic. So that's just, again, another kind of decision. You can easily detect overflow through programming. For example, if we have something like we do this unsigned addition where we're adding, from some source register, we're adding some positive immediate, we know that the solution should be larger than the RD should now be larger than RS. So we can just compare the RD and RS. If for some reason the result is smaller than the original RS, then we have an overflow, and then we can go and take care of that overflow. So we don't need to have this, we don't need to necessitate an overflow check on integer arithmetic. Another thing is that the two LSB bits are always 1, 1. So out of those 7 bits that we have for the opcode, the 2 bottom ones are actually not used in general. They're always 1, 1. And if it is not 1, 1, that means we have compressed instructions, which we'll be discussing in a moment. So in general, the 2 LSB bits are always going to be 1, 1. That easily shows us if we have to decompress instructions. And we will never use all 0s or all 1 instructions. That's just a kind of a decision. So I've said this word extensions a lot, but the motivation for this is that, as I mentioned at the beginning, RISC-V is supposed to be one instruction set architecture that's supposed to be used for everything, for general purpose computing, for embedded computing, for accelerators, and so forth. So you have a tool chain that's been developed and stable and so forth, and you can use it. You don't have to define a new architecture for each type of little accelerator that you make and make a compiler for it and so forth. You can just use RISC-V. And therefore, we made this lowest common denominator that's the base integer architecture, and it's very small and simple and has very few instructions and so forth. And we can just make a basic accelerator that supports that. It's a very small footprint, low power, and so forth. And it must be present in all implementations. But then if we want to go and do special things or additional things or make things stronger or go support high performance computing, then we will add functionality through what we call extensions. And there's a lot of instruction encoding bit space that has been set apart in order to do this type of extension. And in fact, we can make things like variable length instructions and so forth. So if we take the opcodes over here, which are these bits 6 to 2, because remember, bits 1 and 0 are always going to be 1, 1 unless we're compressed, then you can see which ones have already been used by basic instructions and which ones are set aside for custom instructions. And then you can also go and extend beyond 32 bits and do all kinds of crazy things, overwriting these instructions. But there's actually a lot of instruction encoding bit space that's used for identification. Out of that, we have what are called the standard extensions. And they're generally very useful extensions, such as we saw before, like multiply and divide, or atomic instructions, which we'll be discussing later on in the course, or floating point instructions like the F, D, and Q extensions. And these are very commonly implemented. So, the committee sits together and decides on standardizing these extensions, and they're made in a way that they don't conflict with each other. So you can do an M, A, F, D, Q, and they will all be able to work together. However, if you want to do something special for your specific accelerator or a specific ASIC, you can go and make custom extensions and go and overwrite some of the opcode space that is used for these things. And they can be highly specialized. They can conflict with other standard extensions and so forth. And you can do just about anything you want with that. And that's one of the big strengths of RISC-V, that it was built from the bottom up to support this type of extension. So I'm going to go and discuss some of the commonly found standard extensions. And we started with the compressed instructions, which is the C extension. So in general, RISC-V instructions are 32-bit and they are word aligned. But if we want to use this C extension, then we get half word aligned instructions. So what it does is it takes some instructions that are very commonly used, and it compresses them down and encodes them in an instruction that's only 16-bit long, and then we can therefore fit inside one word, 2 instructions, and therefore we can have an instruction that's 16-bit and followed by an instruction that's 32-bit. So we have this misalignment on the half-word level. So each of these compressed instructions, it's exactly equivalent to some 32-bit instruction. They're not new instructions. They're just a re-encoding of instructions that are already used, where we compress them into 16 bits, and therefore we can save code space. Sometimes, especially on embedded machines, the code memory is really one of the limiters, so we want to get our code size to be as small as possible, and compressed instructions, which are also known as thumb instructions in the ARM architecture, is a very commonly used thing. Okay, this can improve performance, more efficient caching, and other things. So with this extension, 32-bit and 16-bit instructions are mixed freely with each other, and therefore during decode, what we have to do is take the 16-bit instructions, see if they're 16-bit, and again, we can immediately notice that because the bottom 2 bits are not going to be 1, 1. So if we see that the bottom 2 bits are not 1, 1, we know we need to take the 16-bit instruction and expand it into its 32-bit equivalent, and then send it on down the data path, just as if it was a 32-bit instruction, just using a little less code space. Okay, so one of the basics behind how to compress these instructions is that we don't actually need 32 registers for all of our instructions. So we can actually have certain instructions that are compressed that they only use certain registers, x8 to x15. So if we only address 8 registers rather than the whole 32, we can use 3 bits to encode which register rather than using 5 bits, and therefore if we have a 3 operand type of an instruction, it can fit into many fewer bits. We can do that with 16 bits over here. We can do other things that just are very common, like if we're doing kind of a C, like x plus equals 1, then we know that it's like x equals x plus 1. That's something that's done often. So your source and your destination operand are the same, and you can get away with doing basically what would be a 3 operand instruction with only 2 operands. So something like that, c dot add w x8 x10 uses 2 operands, but it actually does x8 equals x8 plus x10. You can also do all kinds of things with the stack pointer and with the return address that are easy to compress. So there's this whole set of instructions that are defined in the compressed standard, which enable us to really reduce code space. So that's a nice type of extension to include into your microarchitecture. The next thing is multiplication. So we said that the M extension has multiplication and division, which are not defined as part of the base integer architecture. In other words, if we just implement the base integer architecture, what we're going to have to do is a type of a shift and add to implement multiplication. So if we add the M extension, we're going to actually put a multiplier inside. So let's just look at what happens when we multiply 2 n-bit numbers to understand how RISC-V decided to implement this extension. Okay, so if we have 2 unsigned integers that we are multiplying with each other, we do this, 213 by 187 equals 39,831, and this is the binary equivalent. If we do 2 signed, we have 2 minuses over here, and this is what happens. And in a signed versus an unsigned, also, we take 2 different numbers, and we get, a different result over here. And the first thing that stands out is that we had 2 8-bit operands here, and we got 16 bits at the product. So the result of a multiplication is of n bits is going to be 2 n bits wide. So if we have in RISC-V 32-bit operands, we're going to have a 64-bit result, and obviously we don't have any register that can store that. So this is going to have to be stored in 2 registers in some way or another. Okay, but another thing that I don't know if you paid attention to, that all of the LSBs, in this case the 8 LSBs, but in RISC-V it will be the 32 LSBs of the products, they're all the same for the unsigned by signed, signed by signed, and signed by unsigned. And it doesn't matter what type of operation we have, so we just use the same exact thing. And therefore, we can reduce the number of instructions we implement in. And if we're only working on, the bottom ones, we can actually save a lot of commands that way. So first of all, we need two instructions for multiplication, first doing the high bits and then the low bits. But for the low bits, we just have this mul, this mul instruction, which is going to store the n lower bits in RD. And that's true. It doesn't matter if the source operands are signed or unsigned. It's going to be the same mul instruction for all of them. Then we have options when we're going for the MSBs, the second register, the 32 MSBs that are mul H, unsigned, mul H, signed, unsigned, for these three options that we have up here. So if we want to do this multiplication, we're going to first acquire the high bits with something like a mul H, storing in the destination registers that's going to store the 32 high bits, and then a mul that's going to store the 32 low bits. Division. So division is a more complicated thing that isn't often talked about that much in different types of computer architecture courses and so forth. That's because it's pretty complicated, and there's not that large a wide array of all kinds of optimizations and things that are done with it. It's also not as common, and division is not done as often. And they tell you, for instance, in RTL, never use a divide operation. It's not synthesizable. And the reason is because what we're going to talk now. So dividing is similar to doing long division on paper, even though we're only having binary. The problem is we don't know if the current remainder is bigger than the divisor. So how do we actually go about doing division on paper? What we do is we take the divisor and we check if it goes into the quotient. So we take the first, the 1,000 over here going into the first 4 bits over here, and then we subtract them and we get 1 as the remainder over here. And then we see that the divisor doesn't fit in, so we keep on carrying down the parts of the quotient until we get something that's big enough over here, and therefore we put zeros on top in the quotient. And finally, when we have 1010 over here, we can go 1000 into 1010, goes 1 time, so we add a 1 over here, do the subtraction, and since we don't have anything left over here from the dividend to carry down, that is our remainder, so we're left with the quotient over here and the remainder over here. So that's really nice, but this problem is that we don't know at this point, when we keep pulling down bits from the divisor, if our divisor is larger than or smaller than the quotient, and if we do it. So the algorithm to do that is actually to first subtract the divisor from the current remainder, or the current remainder that we have. And if it's larger, so if we get a positive number over here, then great. If the quotient gets a 1, and we subtract these two, and we're good, and we again try to divide the divisor by the remainder that we have over here. If we get a 0, what we have to do actually is not only put a 0 on the quotient, but we have to add back the dividend to the divisor to what we had over here. So we just have to keep on doing this until we get something that is bigger than the divisor, where we get a positive remainder on the bottom. So this is an iterative loop, and it means that it actually takes n+1 cycles to do it. And it's really expensive. If we look at the type of architecture, to microarchitecture to implement that, it would be something very similar to a shift and add with multiplication. So we have the divisor register over here, where we would put the divisor in the left half, because it's probably going to be smaller than the entire thing, and it's going to be actually a double width type of a thing. And then we're going to keep on, putting it into the ALU, subtracting, checking what the remainder is, shifting right and adding a 0 or 1 into the quotient that's shifted left. So this is an iterative process that's going to take a lot of cycles. Again, we're talking about n+1 cycles, and that's really expensive. It's much more than a single cycle multiplication or addition. So there are faster algorithms, but of course there's a trade-off between how the algorithm is built, if it parallelizes things, and how much it's going to cost to do. So they do this at different levels. But what we need to know at the ISA level is that the M extension provides us with a div command and a div unsigned command, and that returns the quotient. And then we have a rem command for a remainder, or a remainder unsigned command, and that returns the remainder. So again, if we want to get, and that's similar to C, if we do just a slash, we'll get the quotient, and if we do a percentage sign, we will get the remainder. So it's again a kind of an operation that takes two instructions, but it's actually going to be a multi-cycle type of thing inside our machine. The next extension I am going to go into is floating point. So just to remember what floating point is, it's a definition that's IEEE Standard 754/1985, and it's a very important definition that's actually controversial and has a lot of articles written about it, and you can read about it all over the web. So we basically define something that's called single precision, or in C we call it a float, or double precision, which in C we call a double. And so single precision is 32-bit, double precision is 64-bit. And it basically tells us, how precise, how close to the actual fraction of what we get. In any case, we always start with a sign bit, where 0 means it's a non-negative, that's a 0 or positive, and 1 will be negative, so we added a minus over here. And then we have the fraction and the exponent. So the number is actually going to be minus 1 to the power of whatever that sign bit is, times 1 plus the fraction over here, and I'll discuss that in a second, times 2 to the power of exponent minus bias. Okay, and the number of bits we have over here for single and double precision are written down over here. So first of all, we see that the significant is always normalized. So the part that comes before the dot is always going to be between 1 and 2. And that's similar to scientific notation. When we talk about normalization in decimal, if we had one digit over here, minus 2.4 times 10 to the power 56, that's called normalized. If we look over at these guys, we have we have a zero, a leading zero, and several leading zeros. That's not normalized. We would have to move the 2 over to here and change the exponent in order to make it normalized. And the same is here. If we have 987, we have 3 non-zeros that are leading before the decimal point. That's also not normalized. So what we get in floating point is that we're always going to use normalized. So there's always going to be only one digit over here. And what that gives us is that we always will assume that there is a 1 over here, and we don't actually have to include the 1 inside the fraction. So we can assume that there is a 1 and save a bit and get higher precision. So we don't need to represent the leading 1. We always have the sign bit that's a plus minus, and then we have this implicit 1 over here. And then the fraction is basically all of these bits, which are going to be 23 bits in single precision, 52 bits in double precision, which are a binary fraction of where we are in the significant between, where we are between 1 and 2. And then we have the exponent, and the exponent is, in order not to deal with signed arithmetic, what we do is we have a biased exponent. And that means that the representative here of 0 is not actually by putting a binary 0 over here, but rather by putting a biased number. So 0 is going to be minus something very large, and then the 0 is going to be that very large thing. So in single bias, it's going to be a 127. So to get 2 to the power of 0, we would actually write 127 here, or in double bias, we would write 1203. To figure out what the exponent is, we take whatever this value is and subtract the bias from it. And that's how we're going to figure out the exponent. Okay, so that is how floating point representation is done in computers. And now let's see how arithmetic is done. So addition, we're going to have this algorithm. We're going to first align the binary points, then add the significance, normalize the results, check for overflow, and then round and renormalize. So as an example in decimal, because it usually is, more in our language than looking at binary, we would have this type of an example where we have 9.99 times 10 to the power of 1 plus 1.610 times 10 to the power of minus 1. So what we would first do is align the binary points. So this is 1 and this is minus 1. That's not good. We want to align the binary point together. So we would move the 0.610 we would shift over the dot. So we have 0.016 times 10 to the power of 1. Now these are aligned, and so we can just add the significance over here. So we added the significance, and we get 10.015 times 10 to the power of 1. But that is not normalized because we have 2 decimal numbers over here, and so we need to normalize the result. So we move it, move this over to there, and then we get 1 point something times 10 to the 2. We have to check if we didn't overflow or anything like that, and what we finally have to do is round and normalize. So in this case, we only had 4 fractions over here, fractional decimal numbers over here, and in our architecture we only had 3, so we had to round and decide if we were going from 0015 to 002 or to 001. So we rounded and lost some of our precision over there. So it's very similar in binary. Again, we have an example over here where we have two numbers. We have 1.000 times 2 to the minus 1 plus minus 1.110 times 2 to the minus 2. We're going to first, align the binary points so they're both with the same exponent over here. We're going to then add these two numbers. We get 0.01 times 2 to the minus 1, but that's not normalized, so we have to go and renormalize it. So we get 1.000 times 2 to the minus 4, and if it's okay, we don't have an overflow and we don't need to round it, that's going to be our answer. Multiplication is very, very similar. What we're going to do here, though, is we're going to first add the exponents, then multiply the significance, normalize the result, and again check the overflow round and renormalize. And in this case, we have to determine the sign at the end. So just as an example, with decimal, we have 1.110 times 10 to the 10 times 9.200 times 10 to the minus 5. So what we're going to do is first multiply the significance, and it's really easy because we just take, the 10 plus minus 5, and we get 5. So we know that the exponent over here is going to be 5. Then we're going to multiply the significance, so this times this, and when we do 1.11 times 9.2, we're going to get 10.212, and what we have in our exponent is 10 to the 5 from our previous step. So this is going to be our answer, but now we need to normalize it back, and so we're going to move the decimal point over 1, so we get 1.0212 times 10 to the minus 6, and again, we have to round and renormalize, so we have to get rid of one of those, so we decided to round it down. We get 1.021 times 10 to the 6, and that is going to be our answer. Binary, again, is very, very similar. We have 1.00 times 2 to the minus 1, and this one is supposed to be a multiplication times this, and so again what we do is take the minus 1, add to it minus 2, we get minus 3, and then we multiply the significance, and we get 1.110 times 2 to the minus 3, which was what we found here for the exponent. This is already actually normalized, so all we need to do in the end is we need to figure out the sign, so it's a plus times a minus, and it comes out a minus, and there we get our result. So this is floating point arithmetic, and therefore we need to build some hardware that supports it, and usually in a floating point unit we'll have add and subtract operations, multiply and division operations, but we'll also have reciprocal, which is 1 divided by, we'll have a square root operation, and we'll have casting between floating point and integers. So the hardware that implements this is something like this, and you can see it's much more complex than integer. Usually it's going to take, it's going to have a big critical path, so it's going to take several cycles, but we'll usually pipeline it. As you can see in this example, we kind of can pipeline it by the different steps that we showed in the algorithms above. So when we add a floating point extension to RISC-V, they actually decided to give a special set of registers, so as not to confuse the wiring of the integer, regular integer general purpose registers, where we use them for control and all kinds of other things. What they decided to do is, if you want to have floating point unit, you'll have another 32 registers called F0 to F31 that will be only used for floating point operations. So you will not mix in floating point with general purpose registers, and that's based on the fact that floating point is not used for any type of control or addressing at all. So we'll give it its own registers, they will be separate and so forth, and we won't have to mix it in with the real complexities that we might need to use with our general purpose registers. So we have to have load store operations, obviously, so that's going to be FLW and FSW and the rest of the type of partial load store operations. With arithmetic, again, there are going to be things that start with F, and they're going to be signed or single or double precision, so they're going to have this dot. So FAdd.S is going to be floating point addition with single precision. FMul.D is going to be double precision, floating point multiplication. F_S is going to be single precision, square root, and a floating point. Comparison, we're going to have also comparison that's going to be single or double precision, and we're having with floating point, so it's a floating point equivalent or floating point less than or floating point less than equal. And then there's a special branch condition for floating point that's going to be bcond, which it's going to branch on a floating point condition, one of these guys being true or false. So that's floating point hardware. Additional standard extensions that have been developed over time, there are several of them. There might be more than what I wrote here, or they may be developing more as we go on. So there's quad precision, floating point decimal, floating point bit manipulation, dynamically translated languages, transactional memory, packed SIMD instructions, vector operation, user level interrupts, hypervisor and supervisor level instructions. And when I think of these standard extensions, I just was reminded of many, many years ago when I was traveling around China, and I reached the Huanglao Yao village in the Longji rice terraces, and I met these famous red Yao women who they have long hair. They actually never cut hair or something like that in their whole life, and they're showing how when I used to have some hair, that I could have long hair too, and they showed us this long hair. But then when we looked, they actually, not all of them had as long hair as they were actually showing to us tourists. They were these standard extensions that they were adding to their hair, if you can see in this picture. So I thought that was kind of a cool thing to remember and show a picture of when I was discussing extensions.